Hey everybody. Chapter 1, Section 3, titled Real Numbers and the Number Line, begins on page 16. Some notes first. When you multiply the same number twice, that's called squaring the number. For example, if I do 7 times 7, that's the same thing as 7 squared, and I know that 7 times 7 is 49. So I could say that 7 squared is 49. If I do that process backwards, it's called taking the square root. So instead of doing 7 times 7 and getting 49, this time I'm going to start with a 49. Give you another example of that. For example, what number do you square to get 36? What number do you multiply together by the same thing in order to get 36? Well, 36 is equal to 6 times 6. What this means is that 6 is the square root of 36. I need 2 6s to get 36, so 6 is the square root. That little check mark looking thing at the beginning there, that's called the square root symbol, also called the radical symbol. Sometimes it looks a little different, not just a check mark, but a check mark looks kind of like the division sign if you were doing long division. Both of those things mean the square root symbol. The number underneath the radical symbol is called the radicand. That's just a definition. Okay? Let's look at a few problems. Example 1a. Simplify, remember simplify means get one value or one answer. Simplify the square root of 64. Well, what do I need in order to get 64 when I multiply? When I multiply, I find out that 64 is 8 times 8. So the square root of 64 is one of those 8s. Not both of them, just one of them. Another example, example 1b. Simplify the square root of 81 over 121. When you have the square root of a fraction, take the square root of the top, then the square root of the bottom. So on top, I have the square root of 81. What number do I need to multiply together to get 81? That would be 9. And then I take the square root of the bottom. The square root of 121, that would be 11. So my answer is 9 over 11. I took the square root of the top. Took the square root of the bottom. If I could simplify that, I would, but there's nothing I can take out of 9 and 11, so that would be the end. Now, if you're having trouble remembering things like 8 times 8 is 64, or 9 times 9 is 81, what I want to do on the next slide is make a list of all of the perfect squares, or not all of them, but a lot of them, and then a list of square roots. Okay. In this first column, I've got the list of perfect squares. So 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9. The column over here, the 1, the 4, the 9, the 16, those are perfect squares. And I did all the way from 1 up until 15, and then I added 20 on there as well. You should really be able to know those in your head without having to use a calculator or write them out or anything like that. Okay, it makes your life a lot easier later. If I do all of the perfect squares backwards, I get square roots. So, this one, for example, the square root of 4 is 2, because I need 2 2's to make a 4. The square root of 9 is 3, because in order to get 9, I need 2 3's. Okay? Pause here, finish writing down the rest of that list. Okay. If you try to take the square root of a number that's not a perfect square, you're going to get a decimal. In that case, you need to use the process of estimating a square root. I know that you can plug this into your calculator and get an answer that way, but I need to see these steps on your paper. This is the list of steps for estimating a square root. Find the perfect square above and below your number, and I've got an example here to show you these steps. Figure out which of these your number is closer to, and then take the square root of that number. So, if I'm going to estimate the square root of 34, the number 34 is not a perfect square, so I have to go through my steps of estimating a square root. So, my number is 34. I need to find the square root above that number and below that number. So the square root that comes before 34 would be 25. The square root or the perfect square that comes right after 34 is 36. And if you needed to, you could look at that by looking at that list that you just wrote down from the last slide. So 25 is the perfect square just before, 36 is the perfect square just after. Which of those two numbers, 25 and 36, is my number closer to? Well, in order to get from 34 to 25, those are 9 apart. In order to get from 34 to 36, those are just 2 apart. Okay? Which means that 36 is obviously closer to my number than 25 is. Once I figure out which one's closer, I take the square root of that one. So the square root of 36 is 6. So my answer, the square root of 34, it's not exactly equal to 6 because we estimated, so we put the little squiggly equal sign, which means almost or close to. So the square root of 34 is almost 6. More definitions. A set is a collection of objects. Fifth period algebra would be a set of students. Sixth period algebra would be a different set of students. A subset is a group that is taken out of the original set. So if we had fifth period algebra, boys would be a subset. Girls would be a subset. We're taking those groups out. People under the age of 30 would be a subset, because that would be everybody except me. I'm older than 30. An element of the set is an individual object from that set. So it's not a group, it's just one thing. You are an element of our algebra class. Mr. Borthman, I am an element of our class. Just one single object out of a group. When you're talking about sets, you use braces. You can see them there. Sometimes those are kind of hard to write. You can practice it. We're going to work more with sets in Chapter 3. Okay? All numbers can be put into 5 subsets, and we're going to talk about each of those 5 right now. The first subset are the natural numbers. Natural numbers you can think of as the counting numbers. When my daughter was small and she was learning how to count, she would count 1, 2, 3, 4, 5. She didn't know what a 0 was. She didn't know what negative numbers were. She really didn't know what fractions or decimals were. So the natural numbers are just the counting numbers. Whole numbers are all the natural numbers we just talked about and 0. 0 is included in the whole numbers. The next subset are integers. Integers are everything we've talked about so far. We've got the positive natural numbers, we've got the negatives of the natural numbers, and we also have 0. Still no fractions, still no decimals, but pretty much everything else. Rational numbers is the fourth subset. They are any numbers that can be written as a fraction. So, negative 1/4 is a fraction. 0.5, I can write that as a fraction. That's 1/2. 7, I can write that as a fraction. 7/1. Square root of 36, I can write that as a fraction because the square root of 36 is 6, and I can write 6 as 6/1. Okay? Anything that I can turn into a fraction is a rational number. Irrational numbers cannot be written as fractions. Sometimes it's hard to see, so we use 2 other rules instead. Irrational numbers are decimals that do not terminate. Terminate means stop, so the decimals keep going on and on and on forever. Irrational numbers also cannot repeat. Okay? Can't be a repeating decimal. Some examples of irrational numbers. The square root of something that's not a perfect square. 10 isn't a perfect square, so the square root of 10 would be an irrational number. It would be a decimal that doesn't stop and doesn't repeat. 0.10101000, that's kind of hard to say. That's also an irrational number. That decimal does not stop. See those three dots there at the end? It means it keeps on going. And it doesn't repeat the exact same thing over and over again. This is the symbol pi. It is also an irrational number. If you turn pi into a decimal, 3.141579, and it just keeps going on and on from there. Some smart people actually try to memorize as many numbers of pi as possible, and they spend their whole life trying to remember the first 1,000 digits of pi. You don't have to do that, though. Okay, if we turn this type of idea into a problem, some numbers can be in more than one of those 5 subsets. To which subset or subsets does the square root of 9 belong? Well, the square root of 9 is 3. Okay, and 3 can be natural, it's a counting number, it's a whole number, it's an integer, and I can write it as a fraction, 3/1. So, try to simplify what they give you first. So the square root of 9 is 3, and then figure out what that number would be, and then rewrite it with the original problem in it. So number 9, or square root of 9 is natural, whole, it's an integer, and it's rational. It's in 4 subsets. Another example. To which subset or subsets does 3/10 belong? 3/10 is rational because it's a fraction, and because as a decimal it terminates, 0.3 if I turn it into a decimal. So it's only in one subset, the rational subset. It's not a natural number, it's not a whole number, it's not an integer. Next example, to which subset does negative 0.45 belong? It's rational because it's a decimal that terminates. You get 0.45 and then it stops. It doesn't keep going after that. It's only a rational. It's only in the rational subset. It's not a whole number, not a natural number, but it is rational. The decimal terminates. A couple more of these. To which subset or subsets does negative 3 belong? Well, negative 3 is not a counting number, so it's not natural. It's not whole, but it is an integer, and it is rational, because I can take negative 3 and write it as negative 3/1. I can write it as a fraction. To which subset does pi belong? We already talked about it. I'll explain it again. If you turn pi into a decimal, it's 3.14159.265, and it keeps going on and on and on forever. You don't have the same thing repeating over and over again, and it doesn't stop, so it's irrational. The decimal does not repeat, it does not terminate. Another topic for this section, inequalities. An inequality compares the value of 2 expressions. There are 4 inequality symbols. You've seen these before. Less than, greater than, less than or equal to, greater than or equal to. The way that I remember these, there's 2 tricks that I use. If you turn these symbols into an arrow, okay? See how I can turn that into an arrow, and the symbol turns into the arrowhead? The arrow always points at the smaller number. We'll use that in a second. The other way I remember it, you can kind of think of this as like an alligator's mouth. Okay, I'm not going to try to draw an alligator, but you can think of it as an alligator's mouth. The alligator always eats the bigger number. Okay? So, for example, if I had a 3 and a 4, the arrow points to the smaller number. Okay? There's what it looks like if there was the arrow pointing at the smaller number. And the alligator always eats the bigger number. Okay, so there's the alligator's teeth, and he's really hungry, so he's always going after the number that's bigger. An example of this type of problem, if you could have in your direction something that says compare. Compare means look at two numbers and use an inequality sign between them. In order to compare numbers, the easiest way to do it, turn both of the numbers into decimals, put in the correct symbol, and then put the original numbers that you started the problem with back in for your answer. Okay, here's what that would look like. If I'm going to compare the square root of 129 and 11.52, the first step again was to turn them both into decimals. So if I do the square root of 129 in my calculator, I get about 11.35. 11.52 is already a decimal, so I left it alone. 11.35 is smaller than 11.52, so I put in the less than symbol. But 11.35 wasn't one of the numbers that was in my problem, was it? So I can't use it when I write down my answer. I have to change 11.35 back into the square root of 129 before I make my final answer. This line here, that would be my final answer. It's got the numbers that I started with, and it's got the inequality symbol. Sometimes they're going to ask you to look at more than two numbers. Order means comparing more than two numbers. When you put numbers in order, turn everything into decimals first. Put the decimals in the correct order based on what the directions ask for. Usually they're going to say to go from least to greatest. Then remember at the end, plug in your original numbers. You have to have the same numbers in the question that you do for your answer. Here's what that would look like. Example 5a is asking us to order 3.5, negative 2.1, the square root of 9, negative 7 over 2, and the square root of 5 from least to greatest. Don't miss that. If you put them backwards, you'll get it wrong. So the first thing we have to do is turn them all into decimals. 3.5 is already a decimal. Negative 2.1 is already a decimal. Square root of 9 is 3. I don't need to put 3.0. It's just a whole number there. Negative 7 over 2 as a decimal is negative 3.5. And the square root of 5 as a decimal is 2.3. So I just changed all of them to decimals. Then I have to put them in the correct order. Negative 3.5 is the smallest, then negative 2.1, then 2.3, then 3. Sorry, those got a little close together. Then 3.5. I put them in the correct order, but those weren't the numbers they gave me in the problem, so I have to put the original numbers back in. Negative 7 over 2, negative 2.1, the square root of 5, the square root of 9, and 3.5. Okay? Your practice problem for this lesson, page 20, numbers 9 through 49, odds.